Good afternoon. I'm Colin Toomey, Executive Director for the Data-Driven Discovery Initiative. I'm excited to welcome you to today's Knowledge by the Slice lunchtime chat, generously funded by the Adolf and Felicia Leon Fund, which supports programming and lecture series at the School of Arts and Sciences. It's great to see you all here. Today, we're exploring what's become one of the most talked about topics in science and society, artificial intelligence. AI is transforming virtually every field, particularly within the natural sciences. With me are Sudeep Bhatia and Andrew Zahrt. Sudeep is an associate professor of psychology, and Andrew is assistant professor of chemistry. Sudeep Bhatia studies the cognitive basis of human judgment and decision-making using mathematical and computational models. His research looks closely at what people know and how they use knowledge, applying those findings to models that can mimic human thinking and responses. Andrew Zahrt is an organic chemist whose work is closely tied to automation and machine learning. Through his research, Andrew seeks to create new tools that can enhance everything from molecular function to sustainability. Today, Sudeep and Andrew will briefly walk us through some of the ways AI is changing and challenging their respective fields and research. They'll address the highs and lows while also expanding our understanding of what AI will mean for the future of science and research. After their presentations, we will have plenty of time for your questions. So let's start by all welcoming our speakers.
Hello, everyone. So nice to see so many of you here. It's a strange privilege to be asked to give this talk. I think I was invited because Amber thought of me as an AI proponent or an evangelist, but in reality, I think AI is an existential threat to my field. Okay, let me tell you why. Right now, there's 1,000 startups, 1,000 apps that are offering AI decision aids. I study decision making. AI decision aids, AI negotiation aids, AI tools for group decision making, AI therapists, and few, if any, of them are based in any systematic way on the research that I do, or that my advisors have done, or that anyone in my field does. And let me give you an example. While I was prepping this very talk, right, last week, I got this ad from Gemini. Apparently, I can take a video of myself giving this talk, upload it onto Gemini, and it'll give me feedback on argument style, structure, pacing. Okay, if you're someone who studies argumentation, if you're someone who studies persuasion, communication, several of my colleagues do that, right? If you're someone who studies any of these topics, now you're competing directly with Google. Okay, so when writing this talk, I had to resist the impulse to make it a eulogy and instead find a positive model for my field, right, that it could use to navigate the immense technological and cultural shift that is AI. And I found it in all places in meteorology, the science of studying the weather. And so what I'll do for the next couple of slides is tell you about the history of the science of meteorology and not AI and psychology. Okay, so weather, of course, has been long seen as a metaphor for the mind. It is dynamic, it's chaotic, it's unpredictable, it has weight, it influences individuals and societies and economies. King Lear famously described the tempest in his mind that from his senses takes all feeling. You're all familiar with Cat Stevens, right? He listens to the wind of his soul, and where he ends up, only God really knows, right? Only God knows where Cat Stevens will end up, but we do know where the wind ends up, right? We now have highly accurate predictive models for describing the behavior of wind currents. These models are based on large-scale data, on remote sensing from satellites, and supercomputer simulations. All right, and so unlike individual behavior, unlike Cat Stevens' soul, right, we can predict the behavior of the wind. It wasn't always like this. Both meteorology and psychology have the same origins in the Western tradition in the works of Aristotle. In Meteorologica, Aristotle lays out his theory of the weather. He describes it as the outcome of the interplay of wind and earth and fire. And his explanations for the weather are strangely psychological. Whirlwind originates in the failure of an incipient hurricane to escape from its cloud. Yeah, how beautiful is that? In De Anima, he offers a similar theory of human psychology, right? It's the interplay of emotion and reason. So, for example, weakness of will, and I'm paraphrasing here, weakness of will originates in the failure of reason to escape from the cloud of emotion. All right. Now, both fields actually got their scientific start with the development of instruments. It is instrumentation that creates the science, it formalizes the construct, it standardizes definitions, and fundamentally constrains the scope of the field by telling you what can be measured and what cannot be measured. The earliest instrument for meteorology are thermometers and barometers. Right there you have Galileo's thermoscope. The instruments in psychology came a little bit later. I'll give you two examples. Right at the top is the Likert scale. It's an attitudinal scale. It was developed in the first half of the 20th century. Right there, number 16 and 17 are the first examples of the scale items that I could find in the literature. These have to do with American nationalism and American approval of U.S. interactions with the League of Nations, right? So people essentially are given these statements and they're asked to rate it on a scale of 1 to 5 based on whether they strongly approve or strongly disapprove. And this is psychological instrumentation, similar to a thermometer. At the bottom, you see the earliest instrument in my subfield of psychology, which is decision making. So what Mosteller and Nogi did in this classic experiment was offer people gambles, like chances of winning 2 cents or losing 5 cents. And people would press the green or the red button if they wanted to accept the gamble and play it out, or reject the gamble and not play it. And it was all analyzed in this a machine called the Esterline program analyzer. It's not a computer, it's like a signal processing device. Okay, so these instruments that I've shown on the screen are very local. They're rudimentary, and they're local in the sense that with a thermometer, you can only make measurements in a small region of space at a particular point in time. And likewise, with an attitudinal scale, like the one I've shown you on the top right, you can only measure what's in a given individual's mind at the time when they come into the lab and are administered the scale. Okay, and because, again, instrumentation creates the science, at the start, these fields are largely local fields, right? They're concerned with the measurement of local phenomena, with small-scale observation, with taxonomizing that phenomena. For example, developing taxonomies for different types of clouds or different types of personalities. To some extent, they're also concerned with the exploration of the anomalous, right? Like weird phenomena that they can find, strange weather patterns, or perhaps strange behavioral patterns. Of course, meteorology hasn't been stuck doing just that. After World War II, there was a period of immense technological change, which saw the development of the radar, the geostationary satellite. These are tools for remote sensing, right? They can do real-time observation of precipitation, cloud cover, even temperature. There's also developments in computing. So right here is the Jupyter supercomputer. It came out earlier this year. It's the most powerful supercomputer in Europe. And what it does is it simulates weather patterns based on inputs from satellites and radars, right? And with the result of this, the field of meteorology can offer us precise, real-time, large-scale, global predictions, right, that are used by like nearly everyone, right? Anyone here who checked the app on their phone to tell them what the temperature was, to decide what to wear today, right? Like you're using meteorology, right? It's not just you, it's farmers, it's governments, it's militaries, it's investors, all right? That's the science of meteorology. What is psychology doing? Literally the same thing that we've been doing for the past 100 years, right? Like that item there about the League of Nations, like you could take that and replace it with the United Nations, and that's basically a subfield of psychology, right? That Esterline program analyzer, I've written 10 papers, not using that specific machine, but using that broader paradigm, okay? My field is still stuck in the form of sort of local instrumentation. Now, just to make a quick point, you can still make a career doing weird local observational scientific research, right? So in meteorology, you've got storm chasers. This guy, Charles Tanner, has more followers on TikTok than the National Weather Service. And it strikes me that what a lot of psychologists do is a form of storm chasing. We find weird behavioral phenomena, we track it down, we observe it, we take a photograph, or we measure it. And we may not use TikTok to present our findings, but we use its slightly more sophisticated cousin, TED Talk. But if we want to do more than be a TikTok science or a TED Talk science, if we want to be a science that has real-world global impact, right, we have to do something like this. Okay, so this is where LLMs and AI come in, right? On one hand, they're a threat. They say, look, We can make real-time predictions for naturalistic behavioral phenomena, like how your talk will be received by an audience, right? And they challenge us psychologists to show that our findings are actually useful. And so on one hand, they are a tremendous challenge. On the other hand, they also provide us with the technology, with the instrumentation to address this challenge. Okay, just like radars and satellites enable real-time remote sensing of weather phenomena, in the same way, we can use LLMs to do very sophisticated psychological analysis of real-time behavioral phenomena in the wild, right? You can take GPT and ask it to read every news article that's being published, every comment thread on YouTube, every tweet, and analyze it, not just in terms of basic things like sentiment or word count is what we could do like 5 years ago. You can analyze it in terms of very sophisticated psychological ideas. Ideas like weakness of will, if that's what you're interested in. Now, it's worth noting that existing instruments are still used, that older instruments like thermometers are still used in meteorology. They're used to calibrate and validate newer technologies. In the same way, instruments in psychology, like little rating scales and choice paradigms, can be used to calibrate and validate the observations that we get by applying large language models to code large-scale, naturalistic human behavior. Let me give you an example. This is a paper that my lab published a few months ago. I told you I studied decision-making, right? I study how people make choices. Most of my career has been spent modeling accept and reject decisions over gambles, kind of similar to that red and green button tool that I showed you earlier. What we did in this paper, we went and we actually read over 100,000 real-life choice dilemmas that people make. All right, now of course we didn't read it. We got LLMs to read it, right? But from the posts that our LLMs read, we extracted quantitative structure describing the trade-offs, the attributes, the values, the features that people care about, and we also coded this text in terms of how people are making their choices, right? The psychological mechanisms, the heuristics, the shortcuts, the irrationality that they're using to make these important life decisions. Okay, what this gave us was it gave us a map of the space of real-world choice, the ecological structure of this space. And then what we could also do, what we showed we could do in this paper, is we would combine the LLM extracted structures from hundreds of thousands of real-life dilemmas. We could extract quantitatively the trade-offs and combine them with psychological theories to predict the choices that people eventually make. All right. This is just one example. My lab's doing a lot of stuff in this space, but so are many people in psychology, right? And this is really, I think, an example of how we can use these technologies to address the fundamental challenge that they pose to our field. Okay. LLMs as a form of psychological instrumentation. All right, so I started this talk on a very pessimistic note, and to be honest, I think it is right to be pessimistic. It's at the time of great technological and cultural change that academic disciplines die and others emerge, and I do think it's possible that my field of psychology and the subfield of the study of human behavior can be replaced by a subfield of computer science that is basically atheoretical, right, that just uses LLMs as basic predictive tools for human behavior. And that would be really sad. I think a lot would be lost. Alternatively, my field can grow, right? If we use this new technology to expand beyond the lab, to give it real-world scale, predictive power, societal relevance, we can be as important, as rigorous as meteorology, right? And I think, and I hope that that is the vision for my field that is ultimately realized. Thank you.
All right, hi, I'm Zahrt. I'm in the chemistry department. So today I'm going to tell you a little bit about kind of how artificial intelligence is impacting specifically organic chemistry. I'm an organic chemist, so that's kind of the area that I care about. So you can't really talk about artificial intelligence and chemistry without mentioning the 2024 Nobel Prize. So the 2024 Nobel Prize went to determination
or prediction of protein structure. And what's interesting about this Nobel Prize in chemistry is that two of the people up here worked for Google, right? So they're not working at a chemistry lab. They're working essentially in artificial intelligence. And why this is really important is because it takes a sequence, and from that sequence, it predicts a three-dimensional structure of a protein. All right, so why do we care about that? Well, the three-dimensional structure of a protein determines its function, right? So if we want to study the activity or purpose or anything related to a protein in any context, it's really helpful if we know the three-dimensional information, and then we can make inferences about its activity and how that protein could interact with other proteins or maybe molecules for applications in biology or medicinal chemistry. So what they were able to do is they were able to take this huge database and make over 200 million, I think that number's probably bigger now, that's an old number, but make over 200 million protein structures, which pretty much kind of democratizes this process for making advancements in any area that would require this kind of information. So before this was really, really difficult to do. If you want to do it experimentally, you need special resources. If you want to do it computationally, it's very computationally intensive as well. So the way that they describe this is putting a virtual microscope on every laptop, right? Which is, it's maybe a little dramatic. Maybe they're trying to sell you something about this, but it actually does give you kind of some insight into how impactful this was for the field, as evidenced by it receiving the Nobel Prize in 2024. So this, I think, went from, something that was probably a proof of concept to an established routine tool very, very quickly. And it's made very big impacts in the field, and now anybody working in the space is probably doing something with AlphaFold. So I don't work on proteins. The kind of stuff that I'm interested in is making molecules that do stuff. So to just kind of give you some background about organic chemistry before I get into the specifics here, a lot of organic chemistry is you have molecules, those molecules undergo reactions, and you make other molecules. And you do that process over and over again until you get some molecule that you want because it has a function. Maybe it's a drug, maybe it's a polymer, maybe it's some material that has energy relevance. But the impacts of that are very broad. So if you just look around this room, probably 90% of the objects in this room at some point had an interaction with an organic chemist in the development of whatever it is, right? So this is very general. And organic chemists have been really thinking about how to use computers to make their lives easier for pretty much the entire history of computers. So this is one article that I really like. It's from 1957. So I would argue that's within 10 years of modern computers being a thing, like, computers that actually have computer programs on them. So less than 10 years after that, before individual personal computers were a thing. There was a couple of these Russian scientists who kind of suggested all of these things that what they called this information machine for chemistry would be able to do. So if you look at this, these first two relate to, well, I want to be able to search molecules. I want to be able to search their structure, or if they have some function associated with them. Like if I want to find a molecule that does a thing, I'll be able to search for that kind of information, right? And I would say both of these are around and are something that people just routinely use at this point. They also said that we're going to be able to search reactions. So if I want to take a molecule and turn it into a different kind of molecule, I want to be able to identify methods that can do that in a convenient way, right? And these are all just different instances of that. And this is also something that's pretty routine at this point. If we just want to take molecule A, turn it into molecule B, we can look up ways to do that. But something that I think is really interesting is that the last item on their list, this bottom point here is supposed to have the question mark by it, is that if you give it a compound, it'll just tell you how to make that compound, right? So that's different than having molecule A to go to molecule B. That's saying there might not be a one-step transformation there. You might need to do multiple steps from some set of molecules that you can buy to access the thing that you want to make. And they said someday computers are going to be able to tell us exactly how to do that planning. And I'm giving it a question mark here because I think until recently, whether or not that was going to be possible was, something that remained to be seen. And I would still say we're not there for complicated molecules. But this has been something that chemists have been working on for a long time. So to just give you some context about, how this kind of thing might look, don't these are structures. Don't pay attention to the structures if you don't want to. The important part, is this a laser pointer? Can I use this? Oh, cool. This stuff over here, when you mix them together, it makes something that looks like this. And then maybe you want to take this thing and mix it with something else to make a different kind of molecule, right? So this is the kind of task that needs to be done. And we usually have some logic where we say, well, negative things like to stick to positive things. So if this thing's a negative thing and this is a positive thing, they'll probably stick together and we'll make our new stuff, right? So that is a grossly oversimplified way of describing retrosynthetic analysis, okay? But that's kind of the area that it's called. And this has been around since, the late 60s. So this is E.J. Corey. He won the Nobel Prize for developing the ideas behind retrosynthesis. And even then, he was working on these tools that use heuristics in order to plan synthetic routes. So what that means is it's artificial intelligence that is not machine learning. So right now, a lot of the artificial intelligence we care about is, machine learning. This has expert coded rules that it then uses to automate decision making, okay? So there's a bunch of other stuff that people have developed. So this is just to show you that this has been a constant area of research for over 50 years. But now one of the big impacts of artificial intelligence is that we have things that, for example, instead of the experts having to hard code the rules, the machine can extract the rules, right? So you don't have to have a team of organic chemists hard programming rules into a computer. The machine can gather it all by itself. It can automatically then use those rules to plan these routes. And then we're getting more and more sophisticated methods. So these are essentially treating it like a game. So if you know about AlphaGo or something like this, or like those AI programs that can be like grandmasters, it's kind of similar where the reactions are the moves that you can make, and then the molecules are kind of the intermediary points between the moves. So it's a similar area of technology. So this is one area that's been pretty popular. At this point, there's a lot of different programs that use this. This one particular, Cynthia, that's like a thing that you can buy access to, and it's used in the pharmaceutical industry. The limitations here is that if it's a super complicated molecule that requires chemistry that isn't in the literature, you still can't do it because it's kind of outside the scope of your model. So this is one area that I think is really interesting. Another area that has some pretty interesting kind of historical implications is automated structure elucidation. So what that means is when organic chemists make something, there's no way you can look at a molecule and tell what the molecule is. Typically, we have to do all these different types of analysis on it. We get data, and then it's like a puzzle we have to solve to figure out what the structure of that molecule is, okay? And it's actually pretty hard, and it can take a lot of time. So one of the first instances of artificial intelligence in the form of an expert system, like ever, not just in chemistry, is the Dendril project. This is at Stanford. As an organic chemist, I don't know how I feel about my profession being the first one to be replaced by artificial intelligence, but this is where we are. So what it does is it takes this pattern here, and it can essentially map on, these lines to a structure, again, using expert encoded rules. And there's a lot of different methods that can do this. But what's really kind of interesting about this is I think this is, maybe an area where we need more development from AI. Because I can say, as practicing organic chemist, none of these are really tools that I would say we use routinely, like going from this data back to a structure. The other direction works well, but I would argue it's less useful. And typically, in order to do this kind of work, you need to purify these molecules, and the purification is actually one of the hardest parts. So, one area of innovation is can we go, from data to molecule, and is there some way that we could do this for mixtures of molecules? So those are kind of the holes right now. But if you could do something like that, that's something that every organic chemist in the world would use. So another area that I think is kind of interesting is this idea of learning new reactions. So kind of if we put this together, the first case study was, can the computer plan the route? The second one was, can the computer figure out what you made, right? But one limitation in this process is it's planning things based off of a preconceived set of rules. So in this case, a rule is a reaction. If I want to take a molecule and then eventually turn it into another molecule, it knows all of the moves ahead of time. Those are all of the reactions that organic chemists know, right? But a huge area of organic chemistry is discovering new reactions, right? So that's like inventing a new rule for a game. It's making a new connection between two different molecules. So this is something that is very interesting because it would allow a computer to innovate. So instead of saying, using the world's knowledge of chemistry, how can I most directly make this molecule? It could say, well, if you invent this reaction, you'll have a direct route to that molecule, and then this is where I think you should start with inventing that reaction. All right? So there is some work here in this area, and some of it is actually really early. So this guy, Ivar Ugi, I really wish he was born in an era that had modern computers, because I think he would have done some really cool stuff. But he kind of started this idea of can we take molecules and turn them into numbers and stick them into a computer to predict reactivity? So some people have taken this idea and run with it. Here's where I got to plug our own work, because we also are interested in doing this. And the area that I think is particularly interesting, and so I don't think this is a solved problem right now, but I think the way that we want to go about solving it is to say, well, chemistry is governed by physics, right? It's governed by quantum mechanics. So hypothetically, when we think about things in terms of, as a chemist, we think about the structure of a molecule. We don't think in terms of quantum mechanics, right? I certainly can't think in terms of quantum mechanics, right? But what this graph is representing is this is if you plot a molecule in conceptually, if you plot a molecule in molecule space. This is if you put it in quantum mechanics space. And over here would be if I have some molecule that I'm comparing to, these are similar in quantum mechanics space, but different in structure space. That's what this plot is telling us. So can we pretty much train machine learning models that understand chemistry in terms of quantum mechanics? And then can that find things that would be super intuitive in quantum mechanics space, but isn't necessarily something we can understand in chemistry space? And then one last thing that we should talk about is all of that stuff is, higher level planning, but there's been a lot of practical things in chemistry using active learning routines. So that's kind of if you don't have a lot of data, having the model tell you what experiments you need to run next to best explore the space that you're searching. So this is now, this paper is pretty recent, 2021. This is now used by most process chemistry groups at major pharmaceutical companies. And essentially what it does is it uses a model with an uncertainty to help you navigate space. So the model will be able to tell you, I think this point is good, but it'll also tell you, I have no idea what's going on over here. Maybe we should check that spot, right? So you'll be able to, cover the entire space using a minimal number of experiments. And then once you have a good predictor, predict what the best point is. So that's really been done. This is Abby Doyle. She's at UCLA. So this has really kind of transformed a lot of process chemistry. And the direction that I want it to go is using this kind of stuff for automated platforms. So there's also been a lot of integration of machine learning with robotics. right? So anybody who's done chemistry knows there's a lot of boring, tedious parts of doing organic chemistry. And there's been a lot of effort to automate that to achieve higher throughput and to free the chemists up for the creative parts of the job, right? So this actually kind of allows us to be able to automate these more boring tasks. So if we have a chemist designing things, they can interface with a platform that has an LLM and pass it, human level commands. LLM can convert it to machine level commands, and then it could automatically execute optimization routines and stuff like this. So I think that's really kind of some of the big areas that I think the field is going to go. I think generally speaking, one question I get a lot is, do we think this is going to replace chemists? I don't think that's true, right? I think most of the time when you have like a skilled trade or something like this, really it's automating the boring parts of the job. It's helping you make decision-making skills. Like it's augmenting your ability to make decisions, right? So I would say this is a tool that people can use effectively that's going to be a force amplifier. It's not really going to be a human replacement. That's what I got. Thanks for having me.
All right, fantastic. Thank you, Sudeep and Andrew, for your presentations. We'll now open the floor for audience questions. So the way this will work, just please raise your hand. If you have a question, a microphone will be brought to you, so just wait for the microphone. And let's kick it off. So who would like to ask Sudeep and Andrew a question? Sure, let's start with you. Okay.
Thank you. That was very enlightening, and I love this format. So this is fantastic. I guess my question is more directed at Sudeep, but Andrew might also want to wave in. So my question is, and this is, as far as I know, a big debate right now in the AI science community, is whether AI will also develop worthwhile projects. We know that AI can offer tons of solutions once we kind of direct it in certain areas or so. Tell us, certain decision patterns on a large scale. But can it also take the next step to bring about paradigm shift in scientific fields? Can it direct research projects to say, this is what we really need to study? And I hear different opinions about that. So I would like to know what you think about this question.
Great question. So in my talk, I emphasize the benefits of AI as a form of instrumentation, right? As a sensor, you can go and observe human behavior. It's like having an RA, research assistant, code millions and millions of texts in real time. You can do that. And that's very different to what you're suggesting, which is AI as a form of theoretical development, theoretical synthesis, and maybe creative theoretical development. I think, and I can answer that both as an academic, but also as someone who studies human reasoning, and therefore can compare human reasoning with AI reasoning. As an academic, having played around with AI, for developing ideas, it's I think pretty limited. I would say it's at the level of a first-year PhD student, at least in psychology. Which means it can probably come up with reasonable paradigms, but nothing innovative and nothing revolutionary. As someone who understands human reasoning and can compare it with AI reasoning, I would say that where AI tends to fail is in using its existing rich, diverse knowledge in innovative ways. Whereas humans, at least the most creative humans, are able to combine existing knowledge, say knowledge of the literature, as well as some kind of reasoning process, whether it's causal reasoning, kind of factual reasoning, and also creativity, and also, I would say, social awareness to come up with a project or a paradigm that is revolutionary, that is impactful. I don't think AI can do that. I think in order for AI to do that, you'd have to combine its existing knowledge base with something like a human-like reasoning rule. For those of you who want like a technical version of this, I'd say it needs to be combined with symbolic reasoning processes, which it currently isn't.
I think actually kind of extending on that, I'm kind of curious as far as if you're using LLMs for psychology, but the tools, like the measurements that you would already be making are a bit outdated, as you were saying, then how do you know that those results are accurate? Because in the sense of in chemistry, if you propose some kind of mechanism, you could just go in the lab and actually test it. And if it's like completely nonsensical, it won't work. If it's maybe the right solution, then you get the actual molecule you want to make. But if your tools are kind of outdated, then how do you confirm that what you're getting from LLMs is correct?
No, that's a good question. I would say that we use existing tools to validate and calibrate new forms of instrumentation. So again, using meteorology as an example, you have a satellite image, right, and you want to infer from that the precipitation in a given region, right? Like just straight up, it's probably not going to do so well, but you train it on a little bit of data using standard local observations of precipitation, and then now you've got an image classifier that can tell you with a reasonable degree of accuracy how much precipitation there is in every part of the world given a satellite image of the world. I would think of something analogous in psychology, right? If I've got an LLM reading millions and millions of Twitter posts or news articles or comment threads, right? I don't know if it's going to extract the psychological variable of interest accurately, right? But what I can do is get a subset of those posters and use my scales and my survey instruments and all my old school psychology tools to see what their real attitudes are, what their real preferences are, what their real psychological processes are, and validate and perhaps even train or calibrate my AI model to do that more accurately. So certainly old tools still have a place, but they're not our primary form of instrumentation.
You have another question? Yes.
Do you feel like you'll be called upon to use psychology on the AIs themselves, like to analyze what they're doing and how they're affected based on their origins in sort of human text?
Yeah, that's a really good question. Absolutely. So, AI interacts. So psychology and AI combine in three different ways. One is what I told you about. AI is essentially a tool for psychologists. That's how I'm using it, and that's what I focused on. The second way is psychology as a tool to understand AI. It is a different organism, right? But the formulas and the logic of cognitive science is still applicable there. The third way of actually, the third area in which psychology and AI is relevant is human AI interaction. So several of our colleagues study how humans interact with AI. That's kind of analogous to what, for example, user experience researchers did back when computers came out. So these are the three main ways. The one that you're suggesting, using psychology to understand AI, is genuinely, it is being used and it is being used to improve AI. Again, the question is how much is psychology theory really useful versus how much is just sort of raw, like training, right? If you just get enough training data, do you really need a theory of how minds work? Again, I would say that the answer is you do need a theory, and that's where symbolic computation comes in. If you want the models to be creative, to think outside of the box, to extrapolate to new domains, you need to equip them with human-like reasoning rules. So you need to embed human-like psychology into AI.
I think we had a question here. Yes.
Specifically in chemistry, is AI at the point where students won't need to fully know the chemical equations, since the information processing is already acquired by the AI, it's already there, and you phrase it as skipping past the boring part, and the boring part is sort of what happens in learning, and if the AI can do that information processing, can we analyze without knowing what we're analyzing, or can we be creative without knowing what we're...
Yeah, so I think I'm also the most biased person in the world, right? Because I train organic chemists and I don't want to be replaced. But I don't. It's when I say the boring parts. A lot of the boring parts is a lot of manual work and things you can automate, and I think it's kind of the opposite, right? Because it's freeing the human from the parts that aren't intellectually rewarding so they can focus on the creativity parts, right? And I think and I guess this is kind of related to your question too, with right now, especially in things like chemistry, it models interpolate, right? So what that means is it has the set of things that it was trained on, and it can return things that are within that space. kind of the thing about discoveries is they're not in that space, right? Because they don't exist yet. So that, I think, is where the human can work with the AI. So I think you need to be, I think it's imperative that the practitioner then knows as much as possible about chemistry, because then they can say like, well, give me all the information that's known in the world about this, give me all the information that's known in the world about this, and then you can perform the higher level tasks of connecting seemingly unrelated topics to discover new things. Did that answer your question? Yeah. Well, the other thing too about like chemistry, a lot of it is like spatial information, at least organic chemistry. So it's and that's something that, so I do this thing where like whenever I make a problem set, I put it into ChatGPT just because I'm curious. And it's bad at anything that requires spatial reasoning, which makes sense, right? It's trained on text. It is not trained on three-dimensional logic. So it's actually like, but that's also how chemistry works, is through that like spatial reasoning, three-dimensional logic, that kind of thing. So, I guess we're safe for now. Yes. Sorry.
I have a question that falls in the realm of psychology, but I'd be interested in hearing your thoughts on it too, Andy. So I was having a conversation with a student the other day, and they were sharing the ways in which they use AI for homework. And they say, to be very honest here, right? Students in the room, you might do some of the same things. I don't always go to lecture. I don't always understand it, or sometimes it's boring. So this gets to your point about kind of skipping some of the boring part. But I put the slides, or I put information into chat, and it now has learned how I enjoy learning, and so it gives me information back in a way that is digestible and I can understand it better. The psychological part of this is I'm thinking about the pandemic of loneliness, and part of the value of human interaction is learning to interact with people who are different than us, and who communicate in different ways, who have different experiences, who maybe have different accents. And so then translating into the real world, how do these micro moments that we're having in many ways, similarly, maybe there's no answer to this yet because we need longitudinal data, but how might this contribute to the pandemic of loneliness? Are we conditioning AI to give us the outputs that we want? So then when we go to the grocery store, we don't want to have that conversation with the checker in the checkout line. We're just going to avoid it, and we're going to go to the automated checkout because that's more comfortable and we know how that works and it's within our control.
Well, very, very interesting question. I would say that technology creates loneliness in many diverse ways, and that has been a fact from long before AI was invented. Televisions, even newspapers, printing press, I don't know. I wonder if AI is different to these existing tools that automate actions that would have otherwise required another human. I think it is different in one important way, is that AI, unlike a television set, unlike Amazon search, it can mimic the emotional and empathetic responses that we expect of humans. And so what we now see is the growth of AI companions, romantic, sexual, it is very, I was in a committee meeting yesterday supervising a postdoctoral researcher who's working on the effects of AI companionship, and what he finds, Duncan Folk, by the way, he just started at Penn, what he finds is that in the short term, interaction with an AI companion actually reduces loneliness, or reduces, I don't know if loneliness is the right word, but it has a positive social impact. But in the long run, there is a decline in that impact, right? Decline in, let's call it, social well-being. Probably not that different to how someone might get addicted to a drug that then prevents them from pursuing other more wholesome forms of reward. I think AI is similar to existing technologies in many ways, but it is unique in this very particular way. And I have no idea how that's going to work out in the future.
I have thoughts about that too. So I almost kind of think that this is like an issue that, like, as educators, we actually could do something about this, right? So like the way I think about it, and it's tangentially related, but like, it's kind of like, it's a tool and we need to teach people how to use it responsibly. And maybe like, using it to have like an AI companion, or using it to do all your homework for you, or something like that, like all these areas, that is an irresponsible use of the tool. So the way, I guess, I see it as maybe like, but it could also be an opportunity. So like, instead of having to spend all of my time, going over like the basic stuff, could I instead ask questions that require them to apply that knowledge, because then they can interact with the AI and then use that to do things that, it's pretty much like a lower the energy barrier in order to accomplish some task. And then you can still force human interaction by making them discuss this task, right? So I'm wondering if there's some way that, I guess it would require, like, I'm sure there's probably analogs of this in psychology. That's just how I think about it in chemistry. But like, if you restructured the educational system a little bit, could you do it in a way that encourages responsible use of AI as like a side effect? Yeah.
Yes.
Hi, thank you so much for this talk. While I have the mic, I'm just going to go ahead and plug it. I work at an organization that produces socio-technical research on subjects like this, and we actually have a workshop call for applications that's due next week on the craft of science with AI. So if anyone is really interested in continuing the conversation, I would recommend either talking to me later or going to our website, which is datasociety.net. But I do also have a question, and you talked a little bit about AI and labor in your respective fields and how it kind of does or does not pose a threat to your current structure of employment or your professions. And Sudeep, you talked a little bit about using old tools to recalibrate new ones, and you mentioned like the Likert scale specifically, but I was curious if that kind of extends to the researchers themselves, and if you see yourself and your colleagues see yourselves as doing the labor of calibration as like unpaid labor that you in some ways actually pay for, maybe not directly because you work at a university, but somebody's paying to get access to these tools. So is that something that like crosses your minds in any way?
I have a clarifying question. So with like calibration, so let me know if I'm like on the wrong track here. So in my mind, that like calibrating a tool means like comparing it to an established ground truth. Mm-hmm. Is this what you mean by that?
That's how I use it.
Okay.
Yes, in the same way. So comparing it to a ground truth for something that maybe the system itself doesn't.
Right. Yeah. So so in our area, that's actually like really hard. So in a lot of like the high profile areas of AI, like, Chat GPT or something like that, it's trained on like the entire internet or something, right? So it's like, it actually has a pretty good representation of like, like text space. Chemistry is not like that because nobody publishes negative things. So a lot of times, like our ground truth is not readily available. So then we would have to like actually evaluate the ground truth ourselves. And that is like very, very expensive in like, just like the equipment is expensive, the labor is expensive, the chemicals are expensive. So that's actually something that I think is not something that exists in our field right now because the barriers are prohibitively expensive, but I think it's also probably one of the biggest barriers towards, this is why I think you haven't seen like a tool that has like Chat GPT level impact specifically for organic chemistry, is because like we have a lot of holes like in our space. So I don't know if that actually answered your question.
Well, I would say across the sciences, AI has been trained on the scientific literature, right? And therefore, it has learned from our labor, right? To use that loaded word, it has learned from our labor, like facts about the universe, about humans, about, chemistry and psychology, that we've discovered. Now, is that a replace? I sensed in your comment like a question about, is that like somehow exploitative, or is that something to be worried about? And I would say no. I am very happy for someone to read my papers. Not enough people read my papers, and so if AI is able to read it and digest it, and 2 years from now, like some researcher is thinking about something that I've done in that space, and AI is able to sort of say like, hey, like you want to, look at this idea. I'll be very happy to do that, and then if that that means that I have to go to fewer conferences and present my work and write fewer papers or whatever, to do less of the marketing, I'm very happy with that. Now, of course, that's not how it always plays out. I think if you ever talk to AI, it's not always using scientific literature. Like that tool that I showed you earlier where Gemini analyzes your presentation, that's not based in any explicit sense on literature. I would want it to be based on the literature, but it's not. So instead of exploiting or taking our labor, it's sometimes replacing it with something that I feel is inferior.
I think we have time for one more question. In the back. I think I saw his hand first.
Hi. Hello. Thank you. I really enjoyed this presentation. I have kind of two questions. So my first question is, when you were mentioning, Andrew, about how AI potentially will be used to get rid of kind of the boring, repetitive work, and then people can take over more of the more high-level creative tasks. That's not really what we're seeing in its application in other areas. So what would be the belief for why it would be different with chemistry?
Yeah, so in that is largely what I think about AI with automation. So there's a lot of time doing manual labor that's not intellectually rewarding. So that kind of thing is such a high percentage of, someone's typical workday, that anything that could be used to eliminate that, I think, would be adopted really quickly, because it's not fun to do. The task is not fun, and it doesn't really engage you in the way that you would want to be engaged if you entered that field, right? So I think that's and there's a pretty big, just talking to people who work in the industry, there's a pretty big want for this kind of thing. I think if it worked well, that would happen. Maybe, can you tell me a little bit more about when you talk about the boring tasks? So I think you're talking about maybe the intellectually boring tasks. Is that right?
It could be intellectually boring tasks. It could be things that are repetitive, because I think someone else mentioned repetition is also how a lot of people learn. So if it is replacing that, then how would you get to that higher level of understanding in order to do those creative tasks, or even conceptualize those creative tasks? So if it's already replacing those high level things, and then we're saying, oh, it can replace the repetitive things too, then where is the line? Where's the difference?
Yeah, the way that I kind of think about it, so I think there's kind of two issues here. One is about maximizing productivity in a research environment, and one is training scientists. Right? So the part about maximizing productivity in a research environment, I don't really think that you would have, most of the repetitive tasks are things, I think, that removing them from somebody's work will not hurt their ability to think as a chemist, right? There will be some skills, I think some technical skills could be missed, and I think that could have a negative impact on the field. We're seeing this with glass blowers right now, making custom glassware. It's really hard sometimes you need a glass blower, and it's really hard to find one. We have one here, but it's so that kind of thing I could see being a problem with as far as technical skills go. Conceptually, training new scientists, so much of our field is not amenable. It's a lot of it is drawing pictures, right? And that's not something it's very good at. So I don't really see that being something you could replace, but that's, like I said, when you're training new scientists, that's pretty much all they do. But once you're actually doing the job, it's a pretty small percentage of how you spend your time. So I think that there actually could be a pretty good balance there, where it's you can maximize your research productivity without kind of hurting how people think about chemistry. Did that answer your question?
Yes.
I'll add that maybe in the hard sciences that replacement is less likely, but certainly in the social and I would say the sort of humanistic areas, right? If you've got an AI that can just read a book for you and summarize it for you, or just can write an essay for you, you're missing out on critical skills. And psychology, my branch of psychology isn't as affected, because I just work with mathematical models mostly, but certain areas of psychology are, and I'm sure certain areas of other fields are as well. So what to do about that? That's a challenge. That's a pedagogical issue, I would say. We're thinking about it. There's like committees and stuff going on at Penn, but it is, I think, a serious challenge.
Okay. Okay. Thank you so much. So it's time to conclude today's program. Thank you to our presenters one more time. Okay. To see a replay of today's lecture or any other talk from our library of lectures, visit us on the Penn Arts and Sciences website or the Penn Arts and Sciences Vimeo library. And thanks to all of you for coming today to today's Knowledge by the Slice. Thank you.